Thank you very much. So I'm Richard Conway.
Hi, I'm Sandy.
I think the talk title was actually Azure Databricks monitoring 1,000+ solar farms with deep learning pipelines with structured streaming, but we couldn't actually fit it on the slides, so we shortened it today. So maybe some people have actually not made it to this talk. Let's hope so. So just a little bit about us, because it will explain why we've done the sorts of things that we're doing, because you're going to hear a little bit about the business principles, the business outcomes that we started with this project. Some of you may have actually saw we released a video at the advent of Azure Databricks back in March, which talked quite a lot about what we were trying to do in the renewable space. If you haven't seen it, it's on the Databricks website. It's a great sort of rendition of what we did. We are through and through Azure and Spark people. We've been using Spark since version 0.4. We've been using Azure much longer, for about 8 years now. So the fusion of Azure and Databricks has created so many possibilities for us that we didn't have before. Principally, we do quite a lot of community work, and so from both aspects of data science and data engineering and the Azure cloud, we're pushing back a lot of this knowledge into our community. So I'll tell you a little bit about what we're going to discuss today. I'm going to take 10 minutes and I'm going to tell you a little bit about the problems that we're trying to solve, and then Sandy's going to show you how we solve the problems. So we're going to talk a little bit about the solar and renewable space. We're going to tell you how we approach this problem in Azure and what fundamental designs we came up with. We're going to talk about how we use Databricks, because it's really central to this story, and all of the sorts of future orchestrations which we're going to put in place for this platform. So let's start with some basics. This is a solar farm, and I've chosen a couple of very, very boilerplate images just to show you how unbelievably diverse solar farms are. This is one of two solar farms on the left that I thought was quite funky. The Chinese create these really funky looking solar farms. One of them was in the shape of a panda, so I wasn't quite sure whether I was going to show this. This one is an incredibly large floating solar farm. So this is a seaborne platform that they've created to house all these photovoltaic cells. So there's a lot of innovation in this, and it just really brings home the fact that we need land. And we need to understand the economics of this, especially, and how valuable that land is in putting these photovoltaic cells in place. And you can see on the right there that we've got these solar cells, these photovoltaic cells. They're capturing the sun, and you'll find that in different solar farms, based on the topology, they'll be at slightly different angles, but they'll be set once. It's actually quite there's a science behind laying out the solar farm to try to get the maximum amount of production as possible. And it's all about trying to create more and more marginal benefits. So you'll have the land being used to pasteurize sheep. There's a lot of newer solar farms that are actually growing mushrooms in the space under the cells. So it's all about trying to maximize your income within this space, not just from the solar cells themselves. This is a map of what the installed capacity looks like. So you can see that that in the West Country we can expect quite a lot of solar irradiance and production in wattage. But realistically, even though the government has got very, very high targets for this in the UK, it's nowhere near the level of installed capacity as wind. So if you look at these two maps that are side by side, you'll see that the onshore wind, showing all of the brown bubbles, the installed capacity is absolutely tremendous, and that's not including the offshore wind, which is equal or a little bit greater than that. And then you can see that in the south you've got still quite a lot of solar, all concentrated, but nothing near the level of wind. And one of the problems that that a lot of investors are finding at the moment is that because feed-in tariffs and subsidies are changing in this market, nobody's exactly quite sure how much money they're going to make and whether it's worth the investment. And this also varies country by country. So I'll tell you a little bit about the science, and then we can talk about the business. So collecting power from solar panels is actually relatively simple. We point the solar panel towards the sun. We collect the sun's rays in the form of what we call solar irradiance. That is like a big transistor, and it gives us a direct current. We have to convert that so that we can put this onto the grid, and then we can sell in and feed in energy into that grid. Simple. The thing that's not so simple when we started this was understanding that the data acquisition part of this was so complicated. And one of the things that you'll find is that solar farms have been around for such a long time, but because they operate on the margin, all of the normal things that you would think you would put in place to get telemetry out of, they don't have. So one of the problems that we faced was trying to understand how we could put forward an improved business case just to get the telemetry out that we needed from all of these photovoltaic arrays. So one of the things which works really well here, and I just want to talk through this, is there's a protocol called Modbus which operates within the farms, and we need to pick up things like efficiencies of inverters because we need to understand how this energy is being converted, to understand what the production ratios are that we're putting back into the grid, and whether whether we've got any kind of failures within this. And so this is actually quite a nice simple protocol. It's a TCP-based protocol, so we don't need any RS-432 ports, any of the old sort of stuff that you'd find on a BBC Micro where you had to plug in ribbon cables, and that's what you used to have to do. Now more inverters are attuned to Modbus. And generally you have one Modbus connection through your consumer. Some farms actually have a redundant connection as well on another TCP port. But generally what it means is that you can pull out data every single minute, and then you can build a hub and spoke topology and then relay that to the cloud. And you can see here the Modbus definition files are really not that difficult to understand. You get different types of messages, you get the units that these messages are pushed out on. Because this is based on SCADA systems, you effectively have a set of registers, so programmatically they'll send back all kinds of things about inverter efficiency and other attributes. And then with this definition we get our metrics, lots of them. So with inverters, with something called pyranometers, which takes in the energy from the sun and gives us a measure. So what does that solar irradiance look like? What are the PV cells actually taking in? Then generally you have an on-site weather station. It's not great. It's never going to be as good as Met Office data, but it is on-site. And you'll find that generally the weather providers collect weather data from tens of thousands of weather stations, but they're dispersed. So you have to effectively triangulate to try and see where the solar farm fits within all of these weather stations. And then you have an export meter as well. And the export meter is the last point where the energy gets put onto the grid. So at each point where it goes through the farm, you end up with losses because that's the nature of electricity. So we want to understand what gets put onto the grid. Now when we approach this problem, there's a couple of implementations. There's this beautiful implementation where you can actually push data through Modbus and you can control where this goes yourself. So on a minute-by-minute basis, you get this beautiful set of metrics and a lot of them. And with that level of granularity, you can do just about anything. But it also means that you've got very, very, very high accuracy on the provenance of the data. Then you've got some third-party suppliers which will give you a lag on that data for 24 hours. So your systems sort of shift at different rates with different farms. And most of them don't have streaming capabilities, so you have to write these really heavy data orchestration techniques to pull in 24 hours of data and they tend to be housed on lower spec servers. And the whole point here is that one of them is a happy path where you can be in control of the data. The other one, not so much. But with what we did, we have to ensure that we have exactly the same interface at the end of this. And that interface is a streaming interface that we convert, whether or not we've got lag. And that is the point where we begin our structured streaming and ingestion process. So we take a variety of other weather sources as well. We take some cloud cover data. We take sunrise and sunset times, which are quite interesting because what they do is they allow us to calculate what the best day looks like using this technique called clear sky. Now, in principle, why are we doing all these things? We're doing all these things to see whether or not we can predict a little bit about the market. So there's other things that we're not going to be talking about today, which we've done that feed into this, but also to understand a little bit more about how much energy the sun's going to produce tomorrow at a particular geolocation, and how much that plant is actually going to turn into energy that's going to be sold back to the grid. So the first thing to say is that generally this industry is driven by contracts that span years called power purchase agreements, and the power purchase agreements take in all of the risk of something called balancing. So internally, you can see here on this graph that production profile generally looks like this every single day. You sort of know that you've got a peak point around about 4 hours of the day. You'll get maybe 70% of the sun's energy falling onto the solar panels, and the rest of the day it's not as much. But between days, and depending on the weather, you can either end up with a surplus or a shortfall. So if you've got a contract with somebody and you end up with a shortfall there, you still have to supply the obligations of that contract, which is where this begins to get very, very complicated for investors, because in doing so, they have to buy back that energy from the market at an unknown price, which could be in half-hourly increments at a point in the day, and it could cost them tenfold more than it would actually cost them if they produced the right amount of energy at that point in time. Okay, so all of a sudden you can see that there are lots of different economic problems in terms of saving money and making money that you can put in place. And the same with producing a surplus. You know, what do you do with a surplus? If you can push this energy into the grid and you know about it, then having that surplus becomes really important, because you might be able to justify economically to say, well, if I understand a little bit more about the market and I want to understand what the maximum system sell price is at a point in time, is it worth my while putting a battery on site, and what's that going to cost me, and then offset that against the whole lifetime of the battery, so that you can understand that you're making market predictions on one side and predictions on production within the solar farm on the other side. So it gets much more complicated than this as well, because the grid itself has to balance. Right? Our national grid has to cover demand, it has to cover supply, and these two things have to be equal at any short point in time. So the grid will also use tariffs to stop you from putting too much energy in at a point in time, and it can say, well, actually, we're going to charge you like £20 if you want to put this energy in. Right? And of course, you're going to lose money then if you put this in. So there's all of these different things. Depending on Brexit, we may have or not have these European interconnects, which we've been working on for years in terms of negotiations with our European partners. So hopefully all of that won't go to hell. But that is all about being able to redistribute energy between the European community, so that one country can sell to another and we can quantify that. So I just wanted to give you a picture of all of the hundreds of variables that you've got in this problem if you're going to calculate what are actually seemingly quite simple things, simple challenges. And now I'll pass you over to Sandy, who'll tell you what we did.
Thanks, Rich. So this is the first time I've heard Richard give that introduction without complaining more about Brexit, so that was nice. So just to get me started, who's used Azure before? Yes, most people. Good. I don't really have to explain these pretty pictures then. So I'm going to talk you through the first model that we put in place, or the first two models that we put in place in terms of the solar industry. So what we found, and it mainly comes back to the fact that that graph that Richard showed you before of the map between the solar irradiance power generators and the wind, there's such a large difference in actual power output. So solar generators don't have to spend as much on balancing. If they're short, if they're long, they don't have to do as much of that because they don't generate as much power as the wind. So wind is much further ahead in terms of their predictions, in terms of saying this is how much power we're going to generate and this is how much money we're going to make, and because we know these things, we can say we know how much our balancing is going to cost, and we can start to think about how we can hedge against balancing and how we can buy early or sell late and different aspects like that. Solar, not so much. So we started off with an irradiance model, which works fairly well, and we then converted this into a power model. So power tells us exactly how much energy each of the solar farms are going to produce. We've got this in real time now, and we have customers on board for it as well. So if we just go quickly through the Azure architecture, we have the top part of the diagram, which is all about the real-time getting weather data, which feeds into our models for our predictions. So as Richard said, we use various different weather APIs. We use the Met Office, Dark Sky, WeatherBit, and Open Weather. The reason that we do this is we aren't sure if there are any trends in when these forecasts are good or bad, whether there's seasonality between them, whether some of them are predicting better in high sun, some are better at predicting UV, which is a really important feature for us. So we take as many weather providers as we can get, capture all of the data, and generally we average this out across different predictions. We run our model across each of the different weather forecasts, slightly tailored depending on what features are present in each forecast, and then we'll average that to give us irradiance and power. The team are also looking at investigating into the seasonal trends between the different providers. So we have Azure Functions, which for those who don't know is serverless. So this runs on a 5-minute trigger. It has a list of GPS coordinates to go out and call these weather APIs and bring back a load of weather data. So in terms of the scale of that, currently we bring in weather data for about 1,200 farms. We aren't managing all of those, but what we want to do is to collect as much data as possible and to see how that can affect us going forward. So one of the big areas that we want to look at is whether we can predict solar irradiance for the entirety of the UK without understanding the solar farms. That will help us balance later on. So all of this weather data is pushed onto an event hub, which is similar to Kafka, and it's then fed into Azure Databricks using structured streaming. The results of that are fed into a data warehouse, and then we can present it back to either ourselves internally or to customers using Power BI or anybody else that's interested. The bottom half of the diagram is all around the data collection from the solar farm. So we have to go through what's called a SCADA, which is a service that the solar farms pay for, and all of the data that's captured on the site is managed and brought into a service. We have to go in and access all of this data, bring it back out. So we do this on a batch pool instead, and we drop it into an Azure data lake. It's predominantly used for training and model evaluation. So we know the actual irradiance values based on weather actuals from these providers after, and we can work out power based on how well our solar farms are performing on turning that level of irradiation into pure power. So I'm going to go through a little bit of the actual architecture in Azure. So we've set up just a sample which shows just about what we're doing. So we have Event Hub sending all of our messages. We have Azure Functions here to pick up. This is just running off a single solar farm at the minute. So it's going out, calling the weather APIs, pushing things back onto the Event Hubs for us, and we can We can consume from event hubs the same as Kafka. They have multiple different consumer groups. So if we wanted to do something that wasn't Spark related, although I wouldn't talk about it here, we can do that as well. It gives us a lot of flexibility in what we want to do. So we can see the throughput for this event hub has stopped, which means my demo is going to break. Great. So this is all the data flowing through into event hubs, which we pick up through structured streaming. So if we talk very quickly through the starts of the models, we have our radiation model, which we've kind of pulled back, and we've removed some of the features just so we could give a quick overview of it. We care a lot about UV and seasonality in here. One feature that's incredibly important to us, which Richard picked up on, is the concept of clear sky. So what this gives us is a value if weather conditions were perfect. So all we're doing is predicting based on everything we've seen previously, and there's also an algorithm that we've implemented as well. It's recorded and there's papers on it. You can just search for clear sky. You can calculate the value of irradiance that you would receive at a certain point on the ground at a certain angle. So most of our panels are angled at between 20 and 24 degrees in the UK, I think. So we can generate a prediction straight off the bat if conditions were absolutely perfect. No cloud cover, no rain, nothing like that. We know exactly what that value would be, and that's one of the most important features to our model, as well as UV indexing. So what we're using for the model predominantly is UV, clear sky, as well as the seasonality. We train based off 3 years worth of data for each farm so that we can cover as much of the seasonal trends as possible. We have started collecting 10 years worth of data now, so we can train further off this. And for the irradiation model, we use a gradient boosted decision tree, which we can see just at the bottom here. So one aspect that we found incredibly important whilst predicting for solar irradiance was our test train split. We had a lot of problems in terms of getting really good model performance in training and testing, and then getting really bad model performance when we were in production. We found 2 reasons for this. One of them is that UV index is something that seems really hard to predict. None of the weather providers are able to predict this very well. And the second we found was to do with the way that we were training. Originally, we were just using a random split of 70% for training, 30% for testing. We changed this to a temporal split instead, so that we could make sure that we had a full time series of data, and we gained about 10% model accuracy in production. So we were getting about 92% in training and about 72 in production when we first started. And just changing to a temporal split gave us about 10% extra. So you can see we do our temporal split just here. So we do it just off of date time instead of just a random split like below. So this gives us an accuracy off this model for 82%, which is okay. It was one of our kind of cut down models. The next part that we have to look at is power output. So solar farms are they're different in terms of how well they change irradiance to power. Part of this is to do with age, and part of this is to do with just the manufacturers and the different solar panels they have, and inverters and aspects like that. So one of the issues we have with predicting irradiance and power across the entirety of the UK is if we don't have access to a solar farm's actual data, we can't say how efficient they are at turning irradiance into power. That's one of the hardest parts that we have without that data. So working very closely with different solar generators, this is able to give us a lot better performance again. So our irradiance model was 92% accurate in training, and it was 82 in production. The biggest issue we then had was turning this to power. We dropped to about 70% accuracy then because we didn't understand the solar farms. Now we've changed that, and we have a random forest model based on all of the conditions we know around solar farms to change this. So we start to think about power as well as just irradiation. So we use the same feature sets across both of them, and this model just runs secondly after our radiation model using a random forest, here. And for this, we now get 92% accuracy, and this isn't just predicting percentage power at a certain time, this is predicting actual power coming out of the plant. So it's given us a massive boost in terms of what we're doing. This is about 92% again in dev test, and then in production, I think we get about 87% at the minute. So it's been a big change to us. And then finally, we have our implementation of production, which is almost the same as our training. The only difference is we've moved from testing off batch data to streaming in from event hubs. So the way that we partition our data is predominantly across geo-coordinates, and that's one of the aspects that we're looking in terms of model performance. We want to think about how different models can be tailored either to specific solar farms for irradiance or geographical areas, rather than having kind of a global model like we do at the minute. So we read in from event hubs. We have the exact same feature engineering that we do and load in our data from a stream. As I thought, I can't show you the nice bell curves that I was supposed to be predicting. So this morning I had nice bell curves showing the actual solar radiation and the actual power, but that's decided to stop working because demos. So I think that's about all I have in terms of code and talking, unfortunately. Are there any questions I can answer? Please. Thank you.
Hi. I'm just wondering if you have, if you have done that in the morning, you can just go in revision history and see the results. If you just want to show it.
Possibly. Some point. Apparently it doesn't want to keep my images. Okay.
Yeah, no worries.
Sorry.
About your architecture, you have mentioned that you use it Event Hub Databricks, and that is SQL Data Warehouse. If there is any specific reason why you use it, the SQL Data Warehouse, instead the SQL Database or Analysis Services?
So analysis services, we have some of our team looking at using analysis services and Tableau over the top of the data warehouse. It's predominantly the fact that we're doing, we don't really report in real time, so DB would allow us to actually stream into using Spark output syncs. We can do this using data warehouse as well, but streaming into a data warehouse is an anti-pattern. You should use kind of big inserts rather than small inserts. But data warehouse is predominantly just for how much data that we store. We like to give access to our reporting team as well in terms of being able to do anything they want on top of the data, and they've set up a few different views using SQL rather than Spark. So we've just set Spark up to create the predictions and push back out as a roll-up into the warehouse. But we had a DB in place before when we were doing a more straight stream into DB.
Any other questions? Awesome. Thanks, everyone, for coming.